At the outset, let me introduce myself as Dr. Arup Bhattacharya, working as Associate Professor in the Department of Metallurgical Engineering and Material Science, Indian Institute of Technology, Bombay. I am working in the area of polymer carbon nanotube composites for more than 10 years. I have started working in this field from my postdoctoral research during 2001 to 2003 in the School of Material Science and Engineering, Georgia Institute of Technology, Atlanta, USA, subsequently at Leibniz Institute of Polymer Research, Dresden. Currently, 5 of my PhD students are working in this direction and 5 PhD students who have graduated working in this topic. Let me thank Indian Plastic Institute for inviting me for webinar edition of the presentation, and today I am going to talk on processing, structure and properties of carbon nanotube based polymer composites. Over the last 10 years, carbon nanotube based polymer composites have gained considerable interest in the academic and in the research community. If you look at the application areas, CNT based composite materials finding various applications as structural materials for engineering applications, conductive polymers and coatings as anti-static or EMI shielding materials, as a thermally conductive materials, overall as a multifunctional polymer composites. But the question is, why carbon nanotubes? If you look at the intrinsic properties associated with the carbon nanotubes, they are really unique in nature. The very high modulus, close to 1 terapascal, very high strength, close to 100 GPa of tensile strength, their unique electrical conductivity and very high aspect ratio make them one of the very outstanding material as a filler material in the polymer based composite materials. Now the question is, how one can make composite from by utilizing carbon nanotubes inside the polymer matrices. There are 3 in general techniques by which one can make polymer composites. The first one is by film casting of suspension of nanotubes in dissolved polymers. Second process involved the in situ polymerization in the presence of carbon nanotubes, and the third process involves melt mixing, and in the melt mixing one can utilize carbon nanotubes by directly incorporating during the melt mixing process or by diluting the master batch of polymer carbon nanotube composites. Let me start giving you a very extraordinary example where carbon nanotubes could improve the tensile strength of the composite material of almost 60% of the pure material. The fiber of liquid crystalline fiber of PBO, polyparaffiniline benz-bis oxazole, which is a heat treated fiber, it shows a tensile strength of 2.6 gigapascal, and 10% incorporated single wall carbon nanotubes incorporated PBO fiber showed a tensile strength of 4.2 gigapascal, which is almost 60% improvement in tensile strength along with increase in tensile modulus. These composites were prepared during the in situ polymerization of the PBO, and later on it was been heat treated in an argon atmosphere in a tubular furnace in order to make them more oriented. The second example regarding the master batch dilution process, which also came up almost 10 years back by Hyperion Catalysis International, and what they came up with a product is the master batch of different polymer matrices which involved nylon 6, nylon 6X, nylon 12, PBT and so many polymers, where they introduce almost 15 to 20% of multi-wall carbon nanotubes inside the polymer matrix. In these particular case, one can eventually find that these nanotubes are of multi-wall carbon nanotubes of 20 to 30 nanometer in their diameter and several micrometers in their length. So the approach is, so this is one of the work that has been carried out in Dr. Petra Pochke's lab, started from 2001, 2002, where this dilution of master batch was utilized as a technique to prepare the composite material. And the protocol that has been followed is something like, in a small scale microcompounder of 4.5 cc microcompounder, which was the Dhaka microcompounder, the polymer, along pure polymer, here in this particular case polycarbonate, as well as the master batch of polycarbonate multi-wall carbon nanotube composites are mixed such a ratio that you could come up with 0.5%, 1%, 2% and subsequently to 5% and so on. So if you look at these composite materials, or rather the master batch of these composites through AFM and as well as ACM micrographs, you could find that these nanotubes at this particular level, they form a very highly percolated structure, spaghetti-like structure and entangled network. And subsequently through ACM microscopy, one can also find that there is a thick layer of the polymer on nanotube surface that actually shows that almost 30 nanometer of diameter of the final diameter, whereas the nanotube diameter was close to 20 nanometer. That shows polymer nanotube interaction in these composite materials. Subsequently, in order to find out that how nanotube network-like structure develops in these composite materials, various characterization techniques were employed. In order to find out what is the electrical conductivity of this composite material, because this has been already mentioned that nanotube, because of this specifically the multi-wall carbon nanotubes, they are metallic in nature, and it is expected once they form a three-dimensional percolated network-like structure, they will show electrically conducting materials in a given composite material. So what you can see in this particular plot is volume resistivity as a function of multi-wall nanotube concentration, and one can find that it is close to 1 to 1.5% is the electrical percolation threshold where polymer composite of multi-wall carbon nanotube converts from insulating to electrically conducting composites. Subsequently, these composite materials were also characterized through rheological characterization. And the interesting thing, what one could observe, that the low frequency behavior in the slope of the low frequency curve in the complex viscosity versus frequency in case of the oscillatory shear, dynamic shear characterization, that between 1 to 2% one can find that there is a increase in the slope of in the low frequency, which actually indicates there is a development of the network-like structure. And these network-like structure, subsequently termed as rheological percolation threshold, is little different from the electrical percolation threshold, which is completely dominated by the multi-wall nanotube network. Coming to the dispersion of state of dispersion of the multi-wall composites in these composites material, one could see that the network-like structure initiated even from 1%, but at 2 to 8% the composite becomes one can see the 3D network-like structure formation in these composites, but overall one can also observe that there are big agglomerates even at 1%, which increasing with increasing concentration of the multi-wall nanotube concentration. In order to understand whether there is a flow induced orientation taking place during extrusion process, we also observe that there is absolutely no change in the state of dispersion in case of the composite material with 5 or 8% multi-wall nanotube when it has been viewed in the flow direction of the extrusion direction or the perpendicular direction of the extruded strand. Subsequently, it has also been observed that the composite material with 2 or 8% which is extruded strand during the extrusion process, it showed that there is a random network-like structure formation, whereas in case of the melt spun fiber, it shows that the composite material, these nanotubes are oriented in the fiber direction. So it actually suggests that during melt spinning process, the nanotubes are oriented in the flow direction, and so which is not achievable during the extrusion process in the small scale twin screw extrusion. There are also reported literature which suggests that the rheological percolation which we are discussing, that there is an onset of fluid-like behavior to or rather the transformation of a fluid-like behavior to a solid-like behavior in presence of the nanotube materials. They are temperature dependent percolation. So these polycarbonate materials of varying percentage loading of multi-wall carbon nanotubes, it showed that the rheological percolation is different when the experiment was carried out at 170 degrees centigrade versus the experiment was carried out at 280 degrees centigrade. So based on all these observation, one can find that there is a difference in the storage modulus versus frequency as well as complex viscosity versus frequency behavior in this composite material. Based on these experiments, it has been proposed that the nanotube polymer in case of the nanotube polymer composite, there are 3 kinds of network structure involved, which are polymer network, polymer nanotube network, and nanotube network. In case of the rheological percolation, it is all the 3 network-like structure dominates the rheological percolation, whereas with the increased concentration, the electrical percolation dominates. It is also good to understand that how they look like. The multi-wall carbon nanotubes and the single wall carbon nanotubes, they are more like an entangled aggregate. Whereas single wall carbon nanotube case, because of the high van der Waals forces of attraction, they form a rope or the bundles. And one can also observe how they are observed through naked eye. So the fundamental problem while dealing with the carbon nanotube materials, while making the composite with the polymer matrix, is the aggregates formation of carbon nanotubes, even if they are individual. If you look at the nanotube dimension, that is, in case of the single wall carbon nanotube, the diameter is 1.4 nanometer and their length is several micrometer. Whereas in case of the multi-wall carbon nanotubes, their diameter is anywhere from 20 nanometer to 50 nanometer and their length is in several micrometers. However, one can observe big clusters aggregate of several micrometers of diameter in case of the polymer composite material. So which tells that dispersion is one of the challenges in case of this material, along with inadequate interfacial interaction between the polymer matrix and the carbon nanotubes. Here I present 2 case studies. Case study 1, which is injection molded polyamide 6 and multi-wall carbon nanotube composite materials, and we have studied the electrical conductivity, rheological percolation, or the rheological characterization in order to find out what is the effect of purified multi-wall carbon nanotube and the functionalized multi-wall carbon nanotubes which was being procured commercially from Nanosil, Belgium. Here is the morphology of thin purified multi-wall carbon nanotubes NC3100 from multi-wall carbon nanotubes and functionalized, amine functionalized multi-wall carbon nanotubes NC3152 from Nanosil, Belgium. We utilized polyamide 6 from GSFC, M28RC. Their viscosity average molecular weight is close to 38,000 and their zero shear viscosity is close to 180 Pascal second at 260 degrees centigrade. These materials are being prepared in a small scale twin screw extruder which is DSM microcompounder, which is a 5 cc of batch size, followed by either compression molding or mini injection molding machine. What one can observe through electrical conductivity measurement, that purified multi-wall nanotube based composite materials as well as functionalized multi-wall carbon nanotube based materials, that these materials, they show electrical percolation threshold anywhere between 2 to 3 weight% in both the cases, whereas purified multi-wall carbon nanotube materials, they show higher electrical conductivity as compared to their functionalized multi-wall carbon nanotube based composites. These conductivity measurements, this AC electrical conductivity measurement, one can find a DC plateau beyond this percolation threshold at 3 weight% over the entire range of the frequency, and one can calculate the DC conductivity from the power law sigma AC is sigma DC plus A omega to the power n, and omega is the critical frequency which also shifted while increasing the multi-wall carbon nanotubes concentration. So one can see the dependence of DC electrical conductivity as a function of multi-wall carbon nanotube concentration, and one can see that the percolation threshold lies in these polyamide 6 composites is between 2 to 3 weight% carbon nanotubes. Based on this observation, what has been recognized that as far as the theoretical percolation threshold, multi-wall carbon nanotube based polyamide 6 matrix should yield an electrical conductivity much lower than 2 to 3 weight% based on their aspect ratio of the nanotubes and based on the theoretical percolation calculation as per Ballberg, which actually suggests that how much percent of the volume percent of the nanotube required in order to form a 3D network like structure if all the nanotubes individually could be exploited in order to develop the 3D network like structure. Our observation, experimental observation in these the electrical conductivity measurements that suggest that here in this case even the percolating structure involved aggregated carbon nanotubes. In order to improve the dispersion, what we have suggested, or what we have taken a procedure, it's utilizing a novel organic modifier where the sodium salt of 6-aminohexanoic acid has been employed to modify the carbon nanotubes through aqueous medium, and the process will be discussed shortly. What we have done, we actually made a mixtures of multi-wall nanotube with NaHA, which is sodium salt of 6-aminohexanoic acid, with 1:1, 1:2, 1:4, 1:10, 1:15 different ratios, and then melt mix with the polyamide 6 matrix. So here is the structure of 6-aminohexanoic acid and their degradation temperature. Their degradation temperature is much higher than 375 degrees centigrade. So it is easier to process with during the melt mixing process, where these modifiers would not be degraded during the melt mixing process. one can find the state of dispersion of multi-wall carbon nanotubes in presence of the NAHA modifier through transmission electron microscopy, and one can see with increasing NAHA concentration the exfoliated nanotubes are visible in the micrographs. One can also find the specific interactions in the Raman spectroscopy, which is a very important technique in order to understand the purity of the nanotube, or rather the crystalline structure involved in the carbon nanotubes, both single wall carbon nanotubes and the multi-wall carbon nanotubes material. In case of the multi-wall carbon nanotubes material, the ordered graphitic structure, sp2 bonded structure, graphitic structure is characterized by the G band, whereas the disordered graphitic structure is characterized by the D band, and the ratio of G and D band characterizes the ordered structure involved in a given multi-wall carbon nanotube materials. In this particular case, one can see that on increasing the NAHA concentration, the G band shifts to the higher frequency, which actually suggests that there is a hydrostatic pressure involved in the nanotube, and there is an interaction between the NAHA and the multi-wall carbon nanotubes. One can also observe that ID-IG ratio is also changing, which actually shows higher ordered structure in presence of the NAHA material because of the debundling and exfoliation process involved during in the presence of the NAHA. One can also find that the DC electrical conductivity in presence of the various mixtures of multi-wall carbon nanotube and the NAHA in the polyamide 6 matrix, and one can find that even at 0.5% the materials become at least dissipative in the conductivity range, and one can find that the percolation threshold actually shifted towards the 0.5%. This actually indicates that the presence of NAHA facilitates network-like structure formation and their retention in the during the crystallization, and subsequently when the material is being solidified from the melt to the solid. So it's basically also suggests that the refinement of the network-like structure of the nanotubes, where more individual nanotubes are being involved in the given network-like structure formation. One can still observe, characterize rheologically the state of dispersion and subsequently rheological percolation threshold of these composites material in case of the polyamide 6 multi-wall carbon nanotube composites, in case of purified multi-wall nanotube, in case of functionalized multi-wall carbon nanotube, and also in case of NAHA modified multi-wall carbon nanotubes. The signature always we observed is the same. That means the terminal behavior. So in case of the complex viscosity versus frequency, there is always an increase in the low frequency behavior in complex viscosity versus frequency plot in a concentration where between 2 to 3%, whereas in case of NAHA modified multi-wall carbon nanotube material, we observe that even with the 0.5% multi-wall carbon nanotube with various mixtures, the slope of the curve of complex viscosity versus frequency increases as compared to the 0.5% based composites of either purified or functionalized materials. So this actually indicates that increase in complex viscosity above critical concentration, there is a shear thinning phenomena, but overall the interesting thing is that one can find that rheologically they are the rheological percolation is being facilitated because of the presence of these exfoliated multi-wall nanotubes. The degradation of the molecular weight of polyamide 6 was also observed to solution viscosity measurements, and the corresponding molecular weight suggests that what has been observed in the rheological melt rheological characterization it has been correlated with the solution viscosity measurements as well. It suggests that NaHA also aids in either plasticization or molecular chain degradation of the polyamide 6. The rheological network like structure formation in these composites was also characterized through dynamic oscillatory measurements in the melt rheological experiments for the purified multi-wall nanotube composites, for functionalized multi-wall carbon nanotube based composites, and for the composites incorporated NaHA modified multi-wall carbon nanotubes. The observation is similar in case of all these materials, which has also been observed in polycarbonate based multi-wall carbon nanotube composites, which means that there is a fluid like behavior to solid like behavior has been observed from the plateau of storage modulus versus frequency plot, and at the same time in case of complex viscosity versus frequency plot, there is a increase in the slope in the low frequency. One can see that the state of dispersion is found to be better in presence of the NaHA. Here in this particular case, 0.5% multi-wall carbon nanotubes modified at the ratio of 1:15 with NaHA has been shown with 3% multi-wall carbon nanotubes with a mixture of 1:4 NaHA ratio, which shows that there is aggregates are there, but the nanotubes are dispersed as a more individual nanotubes in this composites material. We need to understand the mechanism of dispersion of multi-wall carbon nanotubes in aqueous solution. The way these multi-wall carbon nanotubes were modified with the NaHA modifier in view of the fact that any covalent modification would disrupt the electronic structure of the nanotubes and would involve the breakage of the nanotube during the functionalization process. In order to achieve a more exfoliated structure, less aggregated structure of the nanotube before even putting in the melt mixer, what we realize that NaHA might be dissociated as Na plus and AHA minus in the aqueous solution, and during ultrasonication AHA minus will enter into the nanotube bundles, and there would be a penetration or the gap would be created during the ultrasonication process, and subsequently there would be a formation of electrical double layer around multi-wall nanotubes with net negative charge becoming negative, and the sodium ion will be in the solution. So there is a electrostatic charge repulsion between the multi-wall nanotube, which actually is the responsible for the exfoliation process in this particular case in presence of the NaHA. And this has been understood from various measurements, from UV visible spectroscopy measurements, dynamic light scattering, jitter potential, and the pH measurements, which all suggest that there is a electrostatic charge repulsion between multi-wall carbon nanotube materials in presence of the NaHA. But the main difference between the classical surfactant like material and these material involved with the fact that these particular material, they have a middle portion which is hydrophobic, and both their ends are hydrophilic, as compared to classical surfactant materials, which actually has one end hydrophobic and the other end is hydrophilic, and they actually form a micelle at a concentration beyond a concentration which is not being observed in NaHA modified multi-wall nanotube composite material. One can also observe that how the tensile strength, yield strength, tensile modulus and elongation at break being affected on incorporation of multi-wall carbon nanotubes as a function of increasing amount of multi-wall nanotube concentration of different types, purified multi-wall carbon nanotube, functionalized multi-wall carbon nanotube, and as well as NHA modified multi-wall carbon nanotube materials. The modulus seems to be much more affected as compared to the yield strength, and the elongation at break, which is also as expected being decreased in presence of higher amount of multi-wall carbon nanotube materials. Now I am going to the second case study, which involves the injection molded polyamide 6 ABS with multi-wall carbon nanotube composites. Before starting going into more detailed analysis, experimental observation, let me provide a small background of this particular system. Polyamides ABS blends is a commercial blend of triax, and it has a lot of applications in the automotive sector. And in order to find out that whether we can able to make these blends conductive by utilizing a phenomena called double percolation. Double percolation involves that if we utilize a co-continuous polymer blend, and in the co-continuous polymer blend, if these fillers can be selectively localized in one of the phases or at the interface of the co-continuous structure, then the whole composite become electrically conductive. And in this way, one need a much lower percentage of conducting filler to make the composites conducting. So in order to find out that whether this double percolation phenomena is being followed in this particular system, here the blend system is 50-50 polyamide 6 ABS. Before going into that, we also found that there is a percolation threshold of 4 to 5 weight percent in case of the polyamide 6, in case of the injection molded pure polyamide 6. In case of the ABS material, it is 2 to 3% of electrical percolation threshold, whereas in case of the composite material of 50-50 polyamide 6 and the ABS with the various loading of multi-wall carbon nanotubes, purified multi-wall carbon nanotubes, it shows that it actually suggests that there is a percolation threshold of 3 to 4 weight percent. Now, one can carry out this melt mixing inside the twin screw, conical twin screw microcompounder using a different protocol, a two-step mixing process where polyamide 6 being mixed with the multi-wall carbon nanotubes for the 10 minutes, followed by the addition of the ABS, and or vice versa. That means the ABS can be mixed with the multi-wall carbon nanotubes initially, followed by the mixing with the polyamide 6 phase. It shows that polyamides, if we mix with the polyamide phase initially with the multi-wall carbon nanotube material, it actually yields higher conductivity as compared to if we mix ABS with the multi-wall carbon nanotubes followed by the polyamide 6. But however, the whole experiment, this entire protocol, the mixing protocol and the electrical conductivity measurements of this of the injection molded composites of these composition, this suggests that the mere double percolation phenomena cannot be solely explained in this particular case, because there is a migration and the redistribution of the nanotubes in various phases from polyamides to ABS or ABS to the polyamide phase exists, and there is aggregated structure of multi-wall carbon nanotube which actually increases the percolation threshold. We also optimize the processing condition in order to find out that given a choice that we are working with the two-step mixing strategy, where the polyamide 6 being mixed with the multi-wall carbon nanotubes followed by the ABS, we try to optimize the melt mixing time, where actually we found that the 15 minutes, beyond 15 minutes, it is giving at 260 degrees centigrade and 150 RPM of the screw speed, where actually 15 minutes processing time leads to a higher electrical conductivity. It has also been showed that the blending sequence 1, actually the polyamide 6 mixed with the multi-wall carbon nanotubes, followed by the ABS and the blending sequence 2, where the ABS mixed with the multi-wall carbon nanotube followed with the PSX, we can find that there is a difference in the electrical conductivity on various optimized processing conditions. There is, when we are trying to understand that in this particular case also, what would be the role of NaHA, the novel modifier which has been developed at IIT Bombay in our lab, that what would be the possible organizations if we consider the classical surfactant like SDS molecules on the surface of the carbon nanotubes. One can find that they can be actually covered the surface of the carbon nanotubes in various ways as depicted in the picture, and where the polar end will be up and the hydrophobic end will be attached to the nanotube surface. And in our case, we found that the nanotube length is very small as compared to 6 to 8 angstrom, and the diameter of the multi-wall, considering the diameter of the multi-wall carbon nanotubes. So we found that in our case, we need much higher concentration of the NaHA in order to complete surface coverage of the multi-wall carbon nanotubes. In this particular composite material, where NaHA modified multi-wall carbon nanotubes has been used, we also characterized or rather measured the AC electrical conductivity measurement, and it is observed that even at 0.25 weight% of multi-wall carbon nanotube modified with the NaHA of 1:15 ratio, the electrical conductivity, there is a electrical percolation threshold observed, and which coincides with the rheological percolation threshold. So which means that double percolation along with the surface modification of the multi-wall carbon nanotubes, which actually leads to a lower aggregate size of the nanotube, or rather individual carbon nanotubes, could be exploited in this network-like structure formation in this particular composite material. The melt rheological characterization, which shows how the nanotube can alter the flow behavior of the polymer melt. We know from the rheological measurements that there is a scaling law which suggests that G prime, both the storage modulus and the loss modulus, you can find a terminal behavior as you can in the low frequency behavior, and one can actually find that how they are correlated with the frequency. G prime is proportionate to omega to the power 1.3, and G double prime is equivalent to omega to the power 0.97 in case of the pure polyamide 6 material. However, with the addition of multi-wall carbon nanotube, these terminal behavior disappears, suggesting that there is a change from fluid-like behavior to a solid-like behavior. Melt rheological percolation in the case of NaHA modified multi-wall carbon nanotube, we observed at 0.25 weight%, but at the same time we could observe that at the high frequency behavior, the melt viscosity is decreasing in presence of higher amount of NaHA, which suggests there is a plasticization or the molecular weight degradation of the polyamide 6, which has been discussed earlier. And this is actually also found with the other organic salts in case of the PVDF material, PVDF polyamide 6 blends as well. When you look at the morphology of these materials, which is very interesting to see that even in the co-continuous structure, the nanotubes we could see preferentially selectively in the polyamide 6 phase, and they are also being seen to bridge between the two ligaments of the polyamide 6 phase. There is a bead-like morphology also being developed on the nanotube surface as well. We could see the co-continuous structure even from transmission electron microscopic observations as well, and from the solution experiments we could see that the nanotubes are predominantly localized in the polyamide 6 phase, where actually formic acid, which is a good solvent of the polyamide 6, is actually that particular solution becomes black, whereas the ABS which is THF is a good solvent for ABS, where we could not find much change in the color, but at some with increasing multi-val nanotube concentration, in case of the purified nanotube, we could see that there is a change in color from the colorless to the gray kind of color in case of the THF solvent, which suggests that along with the preferential localization of the multi-val carbon nanotubes in the polyamide 6 phase, there is a redistribution or the migration of the multi-val carbon nanotubes even in the ABS phase. We could see that multi-val carbon nanotubes in the PS6 phase of these blends through high resolution TEM images, where the light phase denotes the polyamide 6 phase, whereas the black phase is the ABS phase, and one could see the polybutadiene rubbery phases as well, which has been stained with osmium tetroxide. The crystallization behavior suggests that there is an unusual crystallization behavior in presence of multi-val carbon nanotubes materials, irrespective of the type of multi-val carbon nanotube, whether it is purified, whether it is functionalized multi-val carbon nanotubes, or whether it is NaHA modified carbon nanotubes. One can find the 2 crystallization peak as opposed to 1 crystallization peak in bulk crystallization temperature. There are number of literatures available in this connection. So one of the reasons there is a confinement of the polyamides in between the chain, which is in the confined polymer layer in between the multi-val carbon nanotubes and the polymer or the nanotube is in the bulk. So that's how, and there is a change in the crystalline form as well. There is a transperiodic lamella which is also responsible for this double crystallization behavior. In conclusion, I would say that structure property relationship studies of the carbon nanotube based polymer composites can be correlated with the state of dispersion of carbon nanotubes during processing. A novel organic modifier can be used to overcome the challenges in context to the carbon nanotubes dispersion. Overall, I would like to comment that tuning the dispersion and the interface formation in case of polymer carbon nanotube composites is the key to improve higher mechanical properties and the other properties as well. There are various references from our group, from various other research group. I have given a few literatures which have been published from our group in the recent times. I must thank and acknowledge Department of Metallurgical Engineering and Material Science, IIT Bombay, SAFE, CRNTS, IIT Bombay, Dr. Petra Pochke, IPF Dresden, Germany, Professor Satish Kumar, Georgia Tech, Atlanta, USA, Professor Ajit Kulkarni, Professor Ashok Mishra, Professor Ajay Pawar, all from IIT Bombay, Dr. Praveen Kodgire, who was my former PhD student, and Dr. Surjosh Sarathi Bose, who was my former PhD student, Dr. Pankaj Thambe, Dr. Rupesh Khare, they are all my former PhD students, and the existing group members. And for the financial funding agencies, Department of Science and Technology, India, DMSRD, DRDO, Kanpur, Reliance Industries Limited, Mumbai.